Let's talk about benzene. Benzene is a special molecule because it's flat and it has three double bonds in a six-membered ring. We can draw resonance structures of these and show the double bonds in every position between carbons. You might expect that the bonds between carbons are the same length, and they are. And the bond angles, CCC, are the same as well. So the system behaves like all the electrons are delocalized around the ring. This may follow from just conjugation. There are conjugated systems where the double bonds are longer than you would expect and the single bonds are shorter than you would expect. But the real novelty about benzene comes from heats of hydrogenation. Let's look at what they are. If we take an alkene and we hydrogenate it to an alkane, energy is lost. That's the heat of hydrogenation because the alkane is more stable than the alkene. If we take a series of alkenes and hydrogenate to the same product, well, then we can compare how much energy was given out from the alkene going to the alkane. And since the alkane is the same in all cases, then the difference must be the difference in energy of the starting materials. So really interesting. Let's take that for cyclohexene, we get one value. We take it for cyclohexadiene, we get a different value. And then we take for benzene, and we expect the trend would go one double bond, one amount of energy, two double bonds, two amounts of energy, three double bonds. No, we don't get three amounts of energy back. We get less than three. Benzene is more stable than we would predict. Why is that? Well, because it has aromatic stabilization. Now, this is often taught in terms of the Huckel 4n+2 rule. I'd like to try to persuade you in this video that it's really the Huckel 4n+2 guideline. Where does that come from? It comes from molecular orbital theory. Let's look at the hybridization state of benzene. All the carbons are sp2 hybridized in the plane of the ring, and they bond one hydrogen each. That leaves one p orbital left over, and that p orbital only contains one electron. Why? Because each carbon is used one electron to bind to one carbon, another to bind to the other carbon, and a third to bind to a hydrogen. It has one left over, wondering what to do. So there are 6 p orbitals around the benzene ring. And what do we know about molecular orbitals? Well, if we take 6 atomic orbitals and overlap them, we get 6 molecular orbitals. The lowest energy one, of course, is going to be the one with all the signs in phase. The highest energy one is going to be the ones with all the signs out of phase. And then in between there are states with 1 node and 2 nodes. How you draw the molecular orbitals in terms of the atomic orbitals and what signs you choose to put on the atomic orbitals and whether you should leave one out or not, it's not really so important. If we're forgetting the node of the p orbitals in the first place in the plane of the ring, then the lowest molecular orbital has no nodes apart from that one. And then there are 2 with 1 node. They're degenerate, exactly the same energy. And there are 2 with 2 nodes. And of course, out of phase has 3 nodes. That's how molecular orbitals work. 0, 1, 2, 3 nodes. You go up 1 node every time you go up 1 level. Now let's think. If we fill up the lowest energy one and the 2 degenerate ones which are next, that takes 2 plus 4 electrons. And then any that we put in the higher energy level is in an anti-bonding orbital. And any less than 4 in the HOMO is less stabilization than we could get otherwise. So 2 and then 4 electrons is magical. And that's where you get extra stabilization from the molecular orbital picture. So we can look at a series of similar compounds like benzene and pyridine. They're aromatic because their heats of hydrogenation are less than we would expect. They're more stabilized. But compare benzene with 1, 3, 5 hexatriene linear. Well, no, it's not cyclic. The ends of the pi system don't join up. The molecular orbitals look different. If we take something that's only 2 double bonds in a ring, that's cyclobutadiene, there's only 4 electrons in that. And so if the molecular orbital picture is the same, we don't get that magic stabilization. And it works out that maybe it is approximately the same in some molecules like that. And we can apply this type of reasoning even to anions and cations. So if I take the cyclopropyl cation, it only has 2 electrons and 1 p orbital. So 4n plus 2 equals 2 if n equals 0. And that's cool. That's an aromatic system. If I take cyclopentadienyl anion, how many electrons there? 2 for each double bond, 1 p orbital containing 2 electrons for the anion, total of 6. That's a Huckel system, that's aromatic. If I take cyclopentadienyl radical, has 1 less than it needs. If I take cyclopentadienyl cation, terrible, 4 electron system. If the molecular orbital picture is the same, it's not aromatic, it's not stabilized, in fact it's unstable. Not so for cycloheptatrienyl cation. That's called tropylium. How many electrons in the pi system? Well, the cation doesn't contain any in the p orbital, but there's 3 double bonds, 6. So 6 electrons in a system which joins up flat is stabilized, and tropylium cations are stabilized, but not the radical and not the anion. Oh no, they wouldn't be. Azulene. Azulene is a very interesting structure. The number of electrons in azulene is 6 for the 7-membered ring and 4 for the 5-membered ring. 6 plus 4 is 10. That's a 4n plus 2 number where n equals 2. Azulene is aromatic. It's a very special molecule because crystals of that are deep blue and fluoresce. And there are even fungi. This mushroom from New Zealand, it produces azulene derivatives as a natural product in the mushroom itself. And it's got this glowing blue color. So why does it fluoresce like that? Well, what's a better way to draw it perhaps than the double bonds delocalized around the 5 and 6-membered ring? Well, the way we could do that is a tropylium cation and a cyclopentadienyl anion resonating with the totally neutral form. That resonance allows absorption of light and emission of light at a slightly lower wavelength before it can do anything else. That's fluorescence. Okay, is the 4n plus 2 rule inviolable? Let's look at a few examples. Well, how about naphthalene? Naphthalene is flat. How many electrons? 10, 4n plus 2, fine. What about ace naphthalene then? We add another 2 electrons. No, not fine anymore. That's 12 electrons. That's not a Huckel number. But you can't deny that ace naphthalene has some aromaticity. Its heat of hydrogenation would be less than you would expect from a system comprised of just double bonds, non-conjugated. And the truth is that the naphthalene is aromatic. The extra double bond behaves more like an alkene. What about other molecules that look aromatic, but maybe are not? Perylene. How many electrons in perylene? Well, there's 10 for each naphthalene ring, if you like. 20. Oh my goodness, it's not aromatic, but it plainly is insofar as it's got a lower heat of hydrogenation than you would expect. It's more stable. So the truth is the two naphthalene rings are behaving somewhat independently. How about C60? How do we work that out? Well, each carbon in C60 has a p orbital, and they're not perfectly overlapped, but they're almost perfectly overlapped. So let's give them that. 60 p orbitals, 60 electrons. Is that a 4n+2 number? If n were 15, that would be 4 times 15, that's 60, plus 2, anti-Huckel. But I think C60 has some aromatic character. So it's not aromatic if you define aromaticity in terms of the Huckel definition. If you look more closely at the molecular orbitals of something like C60, it definitely has aromatic character. And that's why I like to call them the Huckel 4n+2 guidelines for aromaticity. You can quite easily find exceptions. Thank you very much to Eric for giving me use of their studio in Southport, UK. I hope that helps with your studies. Thank you very much for listening. Bye-bye.